everyone. In this video, I'm going to give a walkthrough of my final year project, an explainable machine learning framework for real-time electricity demand forecasting and anomaly detection on the airport power grid using some algorithm called Sharp-guided XGBoost. By the end of this video, we'll be able to understand exactly what the system is and why it matters. So, talking about the problem statement, ERCOT grid is the main electricity grid for Texas, and managing the electricity demand at a scale is incredibly difficult. And the current system rely on simple statistic models, and even small forecasting error means millions of megawatts of hours either wasted or dangerously short during peak hours. That translation to billions of dollars is losses every year. Now, some ML model do exist for this, and they are more accurate. But here's the catch. See, they are complete black box. They give you a prediction, but they don't know why they do this. And if you are a grid operator, you can't just trust a number that you don't understand. On top of that, there is no single system out there that combines live data forecasting and anomaly detection and explainability altogether. That gap is exactly what this project solves. Okay, so here is a quick overview of what our project is. The core of the system is the XGBoost model, but with a twist. We added something called Sharp-guided dynamic feature weighting, which is basically like after training out each round, we compute the Sharp value, which tells us which features are influencing the prediction the most, and we feed those values back into the training process to adjust the model. So this is the novel contribution that is not addressed in any existing literature. And the system also pulls the live data from the government API, detects the anomalies using two-layer approach, and presents everything to a streamlined dashboard with an AI chatbot powered and by the Gemini. The final result is we consider the MAP, which is mean absolute percentage error. So from 10.86, we reduced it to 3.86, which is a 63.6% improvement over our baseline. And also the odd square error we got is 0.94. So this is the overall summary of the project I have done. So next, we are going to talk about the literature reviews. So far I have reviewed 7 recent papers related to this, and there are a couple of key takeaways from that. The paper 1 suggests that and uses a Sharp to explain XGBoost prediction for heating load forecasting, but only after training as a post hoc analysis. They never fed these Sharp back into the trainings, so that is the exact gap our project fills. And paper 2 combined with Profit, XGBoost, and CADBoost and got an impressive R square of 0.97. But again, no explainability, no live API, or no anomaly detection. And then some papers have mentioned about LSTM, CNN LSTM, that shows deep learning works well for time series, but the models are even less interpretable than standard ML. The overall pattern across all these 4 papers is that people either need accurate or explainable. Nobody has combined both real-time data and anomaly detection. So that is the one thing that we focus on in our paper. And we could say that is one of the novel contribution of my project. And now let me walk through the issues and challenges I faced during my during building of the project. So first, the data availability. Most public datasets from ECOT were from 2013 to 2015. Finding fresh, daily updating free data took a lot of digging. We eventually found a EIA Open Data API, which is run by the US Energy Department. The second one is the explainability. Adding Sharp to the model is not just a plug and play, making it meaningful. Generating plain text summaries of what that Sharp value actually means require a lot of engineering on top of the ML work. And the third one is real-time integration. Merging two API live is so basically merging two live API streams, hardly handling data delays and mismatches, and keeping everything automated was a real pipeline engineering challenge because both the EIA data and the material data that we used for weather forecasting have different time zones. And then the fourth challenge we faced is the AI chatbot quality. Getting the Gemini chatbot to respond is simple. It is human-friendly language, but and not just dump raw data. It requires a lot of prompt engineering work, and honestly, it's still being refined. And finally, the data visualization part. So deciding how to present complex electricity data to non-technical users was a big challenge. Like what chart to use, or what are all the graphs we can use so that it will be easier for the grid operator to understand what is happening. So this is basically our architecture diagram I have built for the project. So first of all, we have used two APIs. The one is the EAA API from the US government, and the second one is the OpenVenturo, which is from the basically from the open source. From where we can get the temperature, humidity, wind speed, and cloud coverage. The reason why we took the weather data is because let's say it is a very peak hot summer, so of course the AC usage will be very huge in Texas. Or let's say if the temperature falls below 5 degrees Celsius, then the heater usage will be more. So weather will directly influence the amount of electricity that is being produced. So that is the reason why we take the weather data also. So to talk about the data pipeline, once the data is collected, it enters the pipeline stage. Here first we clean the raw data by removing missing or inconsistent value. Then we perform feature engineering, where we create new columns that makes more meaning to the already existing one. Like from the date column, we can say whether it is a holiday or a weekday, or what hour of the day it is, or what weekday it is. So these informations could be gathered just from the table. So that is what virtual engineering is. And then lag features are created, meaning we use previous demand values to help predict future demand. We also merge the weather data with the demand forecast. Finally, the process data is stored in WDB as a CSV format, and the entire pipeline is automated for the daily update. And then comes the forecast engine. In the forecast engine, we first train a standard XGBoost model, which acts as our benchmark forecasting model. After that, we compute Sharp values to understand how each issue influences the prediction. Using the Sharp value, we generate dynamic sample weights so that the model can focus more on the important patterns. Then we retrain the XGBoost model with these Sharp guided weights to improve the forecasting performance and interpretability. And then the fourth one is anomaly detection engine. After generating forecast, the system performs anomaly detection using two-layer approach. First, the statistical residual analysis checks whether the prediction error crossed a defined threshold, like 20. Next, the isolation forest is used to identify unusual patterns in the data with a contamination set of 3%. By combining both these methods, the system classifies anomalies into categories such as demand spike, demand drop, or a normal behavior. And then the fifth stage is explainable AI dashboard. So basically, it is designed to make the forecast system more transparent and user-friendly. In the home page, user can view a 7-day trend overview. In the forecast session, user can select custom dates or generate the forecast up to 30 days. The explainability section displays sharp visualization and feature important charts, helping the user understand why the model made a specific prediction. We also integrated a Gemini-powered AI chatbot that provides plain English explanation and answers questions related to the live forecast or the grid data. And then the sixth is the sector analysis. This module focuses on the sector-wise electricity analysis. It includes monthly EIA retail data along with the Texas sales data. The dashboard further breaks down demand across different sectors such as residential, commercial, industrial, and transportation. This helps the user understand which sector contributes most to the energy consumption. And then the seventh one is step-by-step explainer. To improve the usability, we include a step-by-step explainer module which provides a voice-guided prediction explanation for the user. The user is basically the grid operator who is a non-technical person. It also includes a bar-by-bar sharp explanation where the user can visually understand how feature impacts the prediction. Finally, walks through and makes a decision whether to trust the model or he have to modify the things that the model gave. Finally, all these are displayed in the dashboard using Streamlight, and also for the graph we have used the plotting function. So to give a quick walkthrough of the project I have made, so this is a website. Here the daily details of how much electricity has been predicted and how much has been produced will be displayed here. And then in the predict future demand section, we can see when is the expected peak tomorrow, when is the minimum, and what is the total range of it. We can see it for each hour, what will be the expected and possible range of electricity demand that is going to come. And then for any day we can select and we can give predict this date. And it gives a quick prediction of what will be the demand forecast for each hour. And also we have a tab for unusual events, whether he can see the unusual drop or spike that has happened. So he can analyze what is the reason for this drop or hike, and he can be aware if that same situation might come in the future. Let's say, for example, on March 7th, there is a sudden spike of electricity demand, which is more than what the model have predicted. So let's say the March 8th has a festival going on. So next time the same festival happens, the grid operator will generate more electricity than what the model has given. So for that understanding, he can go through this page and understand what are all the abnormal predictions that the model have given. So this is the AI chatbot that is powered by Gemini. We can ask questions like what can be the demand for tomorrow, when it will be high, what is the reason for that high. So all these basic informations could be asked. And this is the step-by-step walkthrough for prediction for each day. Let's say I selected a date and selected some hour and give build walkthrough. So here first it will have a base of 54,550 megawatts. On clicking play, so with this step-by-step forecast explanation, the grid operator can be easily able to come to a conclusion whether to trust this model or you have to alter few things. So this is the overall project I have made. Thank you.